Hi, everyone. It's Rajiv Ramchand. This is the third session on this series of basic concepts of epidemiology, where I'm just trying to help make informed consumers of all the information we're getting, especially during this time with COVID-19. Today, this session, we're going to be talking about disease severity. So let's just get right into it. So remember that in session two, I shared that for most epidemiologic estimates, we really have to be cognizant of the fact that whoever is in your denominator needs to be eligible for being in your numerator. And I just want to reiterate that point. It's really important, and especially when we're talking about disease severity. So the measure of disease severity that is the most severe outcome is mortality or death. And we use a term called case fatality to understand the proportion of those with a disease or infection who die from it. Now, of course, there are other severity measures, hospitalization, or more or less severe symptoms, but let's just focus on case fatality for this session. So your numerator is those who died from the disease or infection, and in the denominator, you have those with the disease or the infection who died, as well as those with the disease or infection who didn't die. So two things to note: your denominator does not include the entire population. It only is those with the disease or infection. And second, for the numerator, that A, we have to be careful that we only include people who died from the disease. So for example, if somebody with the disease or infection died in a car crash, they would not be included in the numerator because they didn't die from that disease or infection. Now, they may have died tomorrow had they not died from the car crash, but they did die from a car crash, so we take them out of the estimate. What I'm going to share with you now comes from a really great blog post that I reference here from my colleagues at RAND. Right now, in the midst of COVID-19, we're trying to estimate case fatality in real time, essentially. And that's challenging for two reasons. The first of which is called ascertainment bias, where our denominator is likely to be an underestimate of actual infections. What we know about COVID-19 is that a lot of people can develop it and be asymptomatic. That has a lot of challenges associated with it. What that means, though, from a case fatality perspective, is that our denominator includes only those who are being tested for COVID-19. That tends to be people who are seeking medical care, and those who are seeking medical care are those likely to have symptoms or to have more severe stages of the disease. So that's what ascertainment bias is. And what does that mean? Are we undercounting A or B? We're undercounting B. So we don't have a lot of people in the population who haven't yet died from the disease because we're not including them, we're not testing them, they're not part of our denominator. And what does this do to our case fatality estimate? Well, it makes it higher than you would actually expect because our denominator is excluding a bunch of people with the disease or with the infection, and because of that, the case fatality appears higher than it actually is. So just to describe this pictorially, if we have two populations, in the first, 5 of the people who were hospitalized died from the disease. And that's on the left-hand side. On the right-hand side, you have those who are infected who weren't hospitalized, of whom only 1 dies for the disease. So when we add that together, we have 6 out of 20 people, or 3 out of 10 who died of the disease. So our case fatality, our true case fatality, would be 30% or 0.3, which doesn't come out in either of these populations if we look at them exclusively. We have to look at them together. The other reason why case fatality is hard to calculate in real time is a bias known as statistical right censoring, which really just means that there's a bunch of people when we're taking our estimates that we don't know what's happened yet to them. We're going to calculate our estimate at a point in time. There's a bunch of people who are infected at that point of time, and we don't know whether they will go on and die from the disease or if they will recover. And what does this do to the case fatality estimate? It makes it lower than we would normally expect. So this is pictorially describing statistical right censoring. So this is from session 2, the same graph, and you'll see that we have that first person who became infected on the 30th, and when we stop observing on the 31st, they still have the infection, and that compares to the third individual, this guy who got infected for 2 days and then recovered, and then this woman who was infected for 2 days and then died. So who is statistically right censored in this example? Well, it's this top guy. He's still infected when we calculate our case fatality estimates, and we don't know whether he's going to be more like that third individual who recovers or that fourth woman who passes away. What we know about COVID-19 with respect to case fatality, when we take ascertainment bias as well as statistical right censoring into account, we see these ranges of case fatalities around our population across age groups. So for example, our case fatality for, and this, don't necessarily look at the bar chart is interesting. These dark blue represents those who died within each age category. Well, I calculated these case fatality estimates from a table that was presented in this source. And what you see is that, for your under 20-year-olds, the case fatality is 0. You have less than 1%, less than 0.5%. For your 20 to 44-year-olds, then it gets a little bit higher as you get older, but it's still under 1% for your 45 to 54-year-olds, and it increases over time. And so, for your 85 and older, you have 10 to 27% of those who were tested and tested positive for COVID-19 who died from it. So really wide variation in terms of case fatalities, especially with respect to age, that we're seeing so far. I wanted to show, how that compares to some other diseases. And the source for this, a lot of this data is unfortunately Wikipedia, though I looked at their sources. It's just hard to find a list of a bunch of different case fatality estimates, although it is on Wikipedia. So what you see here is that if you have Ebola, you haven't been vaccinated for it, and you do not receive treatment, case fatality can be as high as 90%. If you're unvaccinated for smallpox, case fatality is 95%. On the other hand, if you compare, SARS is 11%, unvaccinated and acquiring measles, it's 3%. But each of these estimates, you have to think of them very carefully. And this is just an average. And what we know for a lot of these, just like COVID-19, there's a lot of variability. So what that means is that if you take the malaria example, in aggregate, if you're infected, less than 1% of individuals die from malaria. However, this paper I linked to below shows that for youth who are infected in sub-Saharan Africa, the case fatality from malaria is as high as 4.5%. So again, think of these as averages, but in average, they don't necessarily give you the full story of how lethal or how fatal some of these diseases may be, or infections. And then just to close, my own research is heavily involved with suicide prevention, and we also think about case fatality. This is estimates from a group of researchers at Harvard who looked at case fatality when you attempt suicide using different means. And so what this means is that if you attempt suicide with a firearm, there's 83% of those who attempt with a firearm will die from it, relative to, for example, jumping, where around a third of the individuals who attempt suicide by jumping will die from it. And drug ingestion, the case fatality estimate is only 2%. And so we used information and data like this to think through how could we use this information to inform our suicide prevention efforts. So that's it. The next session is going to be on herd immunity. I hope this was helpful for you. In the meantime, stay safe, stay healthy, and stay informed. Thanks.